Our KR'24 paper introduces a novel semantics called Collective Satisfaction Semantics, which we apply on what we call Opinion Based Argumentation. This work is part of our efforts to combine abstract argumentation and voting to enhance decision-making tools. This is my joint work with Jérôme Delobelle, Sébastien Konieczny, Clément and Srdjan Vesic. Argumentation frameworks, or AFs, are widely used in e-democracy for structuring debates, and platforms such as KR' are examples of this. In these platforms, participants are allowed to add arguments and to vote on these arguments, but they primarily serve as visualization tools, and they lack any integrated reasoning mechanisms. I have mentioned AFs, and these are Dung's argumentation frameworks. You can see in the example below we have an AF, where the nodes are the abstract arguments, so we have A, B, C, D as arguments, and the edges are the attacks. These are binary relations in between the arguments, and you can see, for example, A attacks B. In Dung's framework, we also have some semantics we can apply on these AFs to obtain the sets of arguments that can be accepted together. For example, if I use their preferred semantics, I obtain AD that can be accepted together and BD. Some additional context. In our framework, each argument represents a belief. So it's a belief-based AF, and we consider that this AF is complete, meaning that all of the arguments and all of the attacks necessary to understand this issue are already present in the AF. Now, let's take the same example as before, and I add to it some voters. I have voter 1 that believes in AD and does not believe in C. I have also 2 other voters. How can I use these voters to refine the results I have obtained from the preferred semantics? This is why we introduce opinion-based argumentation. Opinion-based argumentation frameworks are composed of the AF, so the arguments and the attacks, and a set of votes, which are vectors composed of 1, -1, and 0. So here in the example, voter V1 believes in A, does not believe in B, and is abstaining about C. In addition to the framework, we introduce collective opinion semantics. This is just a general family of semantics that says that the input is an OBAF and the output is a set of arguments. Because we did not find many works solving this issue in the literature, we decided to start by defining a straightforward and naive method to act as a baseline. This is what we call the attack removal semantics. To define the semantics, we use 2 works from the literature. This works in 2 steps. First of all, we calculate the initial weight. This is using the initial weight function from Leite and Martins in social argumentation frameworks. Then, we remove the attacks of the lower weighted arguments using preference-based semantics, introduced by Amgood and KR'. Now we would like to introduce the new semantics called Collective Satisfaction Semantics. The semantics provide a clear metric to measure how well an extension matches to a vote. This method works in 3 steps. First of all, we compare each vote to each extension. Then we can use an aggregation function per extension. So for example, if we want a utilitarian vote aggregation, we can use the sum method. Or if we want an egalitarian method of vote, we can use min or leximin. Finally, we just need to choose the highest scoring extension or extensions. Now let's go back to our operators we introduced first of all. We introduced 3 operators. The first one, satisfaction, which measures agreement with voters by counting how many arguments align with both the votes and the extension. Then we introduced dissatisfaction, which measures disagreement, and it counts the number of arguments where the vote disagrees with the extension. Finally, we introduced utility, which combines both satisfaction and dissatisfaction into a single measure. This is a comprehensive metric for finding the best extension. In the literature, we found 2 works that are more or less related to this issue. The first one by Caminada and Picotti, called On Judgment Aggregation in Abstract Argumentation, and the second one by Bernreiter and colleagues, called Combining Voting and Abstract Argumentation. In our paper, we provide a full comparison of these 4 methods by adapting the 2 related works into COS and OBA frameworks. In addition to the comparisons on multiple examples, we provide an axiomatic study of these 4 methods. We propose a list of 10 properties we divide into essential properties and additional properties. The essential properties all of the method should abide by. This includes properties like non-triviality, where if we apply a semantics on an AF and we obtain a non-empty solution, this means that the aggregation should also give a non-empty solution. Or conflict-freeness, where if 2 arguments attack themselves in the original AF, these 2 arguments should not be accepted together. And the additional properties are properties that are not necessary, but they describe the type of vote. For example, extension majority could be associated with utilitarian methods of vote. From the axiomatic study, we can see that our method, collective satisfaction semantics, abides by all the essential properties. And in addition to that, we can see that our sum aggregation abides by extension majority and continuity, so it is a utilitarian method of vote, and mean and leximin do not, so they are egalitarian methods of vote. To see a full analysis of these results, please check out our KR paper.